Hey there everybody, welcome back. So, in this problem, we have a block on an incline, a frictionless incline, and it's attached via a string that's wrapped around some axle. Okay, and that axle rotates around a central bearing. Okay, so ultimately we want to find the rotational inertia of that axle. In other words, what's the moment of inertia, I, of this axle as a whole. Okay, so it turns out we won't actually need to know what its exact shape is, right? We can't necessarily treat it as a solid cylinder. It's not really a disc per se, it's just some strange shape. But it doesn't matter in this case because we're just solving for I, right? So we have kind of a running theme going here with twos. So we know the axle's radius, 0.2 meters. We know the angle of the incline at 20 degrees, the mass of the block at 2 kilograms, and it accelerates down the surface at 2 meters per second squared. Right? So this is a Newton's second law for rotation problem. So that means we're going to have a torque, and thus we're going to have some moment of inertia and angular acceleration. But we don't necessarily know the force right away. Right? We need to calculate that. We need to knock down the cobwebs from chapter 5 and figure out the force on this axle. Right? So let's draw a free body diagram. So if we have the axle right there, there's a force on it from the rope that's acting, actually let me do it like that. That rope is, there we go, there's a block. That's a bad free body diagram, but I hope you get the picture. That force is acting from the central axis out to where the force is applied. So we have that tiny value of R right there. And the force, I'll do it in red, is pulling down. Right? The force on the axle. And that is perpendicular to R. And that's important here. That's the same force, mind you, as the force of the string pulling up the incline on the block. Right? And if you want to call this tension, you can. Right? Actually, yeah, let's do that. Because it's a string, we've always had those forces as tensions. But the magnitudes of those two are the same, right? So we want to find an expression or even a value for that tension right there. Well, if they're the same as this tension, how do we get that? Well, we have to do the forces on the block. We know there's a normal force and there's a gravitational force down. All right? So that's of some angle theta. And so we can write the forces as their components. This will be mg cosine. This will be mg sine. Okay. So let's get an expression for t, which means we're not done yet with our free body diagram. We have to write out the second law equations. Whoop, I need directions. Let's see. This object is accelerating down the incline, right? So let's put our positive x in that direction, right? That'll help us. So that means mg sine is positive. And the tension is actually negative. But we have a positive MA. That's good. In the y direction, normal force, positive minus mg cosine equals 0. All right. All right. Now, for the axle, right, this whole thing is the system. So this whole thing is the free body diagram. That block is not rotating, but the axle is. So we also need to have a sum of the torques. Okay, so now in chapter 10, when we're doing these second law problems, we have three equations now. Three net force or three net equations. Two for force, one for torque. And so the torque, there's only one torque present, and it's still R cross F, right? And so if we evaluate this, that's the magnitude of R times the magnitude of F, which we're calling tension, and that always equals I alpha. Okay, the net torque always equals I alpha. Oh, I left off the sine of 90, right, in here. Sine of 90 is 1 because they're perpendicular. All right, so we need to solve for tension. I'll use the x equation and get an expression for tension. That gives us mg, I'm going to run out of room, mg sine theta minus ma. And so now I'll take all that and plug it in to the tension in the torque equation. Let's see what we get here. Equals I alpha. All right. And so we're solving for I. So we're basically one step away from doing that. Let's see, do we need to solve for anything else or rearrange in any way? Values for R. We have that. We know the mass. Know G, that's constant. We know the angle. The linear acceleration A, that's what this 2 meters per second squared is. Right? The box accelerates down the surface or down the incline. We know A, we don't necessarily know alpha, right? But we can relate the two together. So remembering that, let's see, the angular acceleration, well, let's do it this way. The linear acceleration is related to alpha by this expression, okay? For that block, or the axle, right, is having some angular acceleration around like that, and it's of some radius, r, which means it has a tangential acceleration of a. Okay, something like that. So using this expression, or this relationship between a and alpha, we can plug that in here and rewrite it like such. Alpha would then be a over r. And now we can solve for I. So we get r squared times what's in the parentheses mg sine theta minus ma divided by a. And we know everything in this expression now, right? And since I don't have room on this page, I'll let you plug in the numbers, but you should get a value of 0.054, and the units for I, the SI units are always kilograms meters squared. And there we go. Okay. Notice that I kind of implicitly put alpha here and these torques as positive, right? That's because this torque here is going counterclockwise. And that's the direction of positive torque. So this torque here was positive, and the net torque was also positive, right? If, for example, if this was switched and that axle was, for some reason, accelerating clockwise, right, you would have a negative in your torque and a negative at your net torque expression, okay? Just like in the forces, just like up here, we put the positive direction of x in the same direction that the object accelerates, right? That makes this net force, ma, positive. And we don't have to worry about a negative out front. Okay? A very similar thing happens for rotation and torques, right? If it's counterclockwise, that net torque is positive. If it's counterclockwise, you have to have a negative sign there. Okay? All right. But that's how you do a second law for rotation, incorporating net forces and a net torque in the same problem. Right? All right. Thanks for watching.